The next example in the class notes on optimization is example number 2. It says find two positive numbers that minimize the sum of twice the first number plus the second if the product of the two numbers is 288. Okay, the challenge in math is oftentimes just reading the question and understanding what it's telling you. So, two positive numbers. So let's let the two numbers be x and y. What is our goal? Our goal is to minimize the sum. Okay, but not just the sum of x plus y, the sum of twice the first number plus the second. So let's write an equation or a formula for the sum. The sum is equal to twice the first number, I'll let x be the first number, plus the second. Okay, and our goal is to minimize that. All right, our secondary equation is that the product of the two numbers is 288. So that means x times y is 288. All right, that secondary equation is going to help me write the formula for the sum in terms of one variable. So I'm going to choose to solve for y. Y is equal to 288 divided by x. Therefore, my sum formula is 2x plus 288 divided by x. All right, and this is the sum that I want to minimize. Okay, so what we're going to do is we're going to find the derivative, because when we find the derivative and its critical points, we'll find possible locations of maximums and minimums. So my derivative is going to be 2 minus 288 over x squared. All right, so just to refresh, I could call my sum 2x plus 288 x to the negative 1. Therefore, the sum derivative is 2 minus 288 over x squared. Okay, I am going to encourage you to write this as a least common denominator fraction. That would be 2x squared minus 288 all over x squared, because it's much easier to find the critical points when the numerator is equal to 0, when the denominator is equal to 0. Okay, so x is equal to 0 is a critical point, as well as 2x squared minus 288 is equal to 0. That's the same as 2 times x squared minus 144, which is also the same as a factor, x minus 12 and x plus 12. And that's going to give us zeros of the numerator as positive and negative 12. Okay, so my critical numbers are positive and negative 12 and 0. On my derivative number line, I'm going to start by putting all of the critical points on the number line. Identifying where this derivative is 0 and where the derivative is undefined. And then I'm going to think about where the derivative is positive and negative. Okay. This is like, I'm going to think about it as a related fourth degree polynomial. All right. x squared times 2x minus 12x plus 12. All right, this is my related polynomial just for the sake of thinking about positiveness and negativeness of the derivative. Okay, so it's a fourth degree. That means it's got to do one of these numbers. Up, up on either end. We've got to have a kiss and run at 0. So our derivative is going to be positive to the left of negative 12, then negative, and positive. Okay, but remember, we have a domain restriction. We want positive numbers. 0 is neither positive nor negative, and negative 12 is not what I want. So I am actually going to exclude everything to the left of 0. And so the only thing I'm going to be looking at is the number line from 0 to infinity. My derivative is negative to the left of 12, positive to the right of 12, which means my function is decreasing, the sum is decreasing and then increasing. So at x equals 12, we must have a minimum. This is a good sign because my goal was to minimize the sum. So I'm going to say sum prime changes sign from negative to positive at x equals 12. Therefore, the sum will be a minimum when x equals 12 and y is equal to 288 divided by 12, which I know is 2 times 144 divided by 12, so that's 24. So when x is 12 and y is 24. And the minimum sum is is 2 times 12 plus 24, or 24 plus 24, or 48. Okay, it didn't actually ask for the minimum sum, but just in case the next problem does. Okay, so putting your answer into words means stating all of this, that your derivative changes sign from positive, negative to positive. Therefore, at x equals 12, the sum will be a minimum. Let's see if we can get one more example in this video. Example number 3. What are the dimensions of an aluminum can that holds 40 inches cubed, 40 cubic inches of soda, and that uses the least amount of aluminum? So right there, least amount of aluminum. There's my goal. I want to minimize surface area. Assume that the can is cylindrical and capped at both ends. So draw a nice picture of your can. It holds 40 cubic inches. So volume V equals area of the base, pi r squared, times height. And that's 40 cubic inches. This is actually our secondary equation. So we'll use that later, probably to solve for h. Okay, what is the equation we want to minimize? We want to minimize surface area. All right, the surface area of this can, we have 2 circles. So that's 2 pi r squared. Plus we have the lateral surface area. If I unroll this can, right, this is the circumference of the circle, so that's 2 pi r. n times h. Okay, so plus 2 pi r times h for my lateral surface area. Okay, there's my h that I would like to solve or to replace so that I have an equation in terms of one variable. So let's go back to our volume equation. Solve for h and write our new surface area equation. 2 pi r squared plus 2 pi r times 40 over pi r squared. Go ahead and simplify that equation to 2 pi r squared plus 80 over r. The factor of pi is going to cancel out, and one factor of r is going to cancel out. Okay, so here's our surface area. Our goal is to minimize the surface area. So let's take our derivative. S prime will be 4 pi r minus 80 over r squared. Get a common denominator. 4 pi r cubed minus 80 over r squared. Find out where your numerator is 0. Find out where your denominator is equal to 0 to get your critical points. So critical points happen when r is equal to 0. Also when 4 pi r cubed minus 80 is equal to 0. That means r cubed is equal to 80 divided by 4 pi, or 20 over pi. Okay, I'm just double checking. All right, and so r is equal to the cube root of 20 over pi. We could use our calculator to estimate what that is. That's about 1.853 inches. Okay, so we have two critical points, and we are going to create our surface area number line with 0 and the cube root of 20 over pi. Okay, thinking about this related polynomial for the derivative to figure out the positive and negativeness, r squared times 4 pi r cubed. Okay, that means it's a 5th degree polynomial, and it's going to start low and end high. It's going to be a kiss and run at 0 and a cubic looking around the cube root of 20 over pi. Okay, so that means my derivative is negative, negative, and positive. All right, so my surface area is decreasing before the cube root of 20 over pi and increasing after, making this a minimum. Okay, and I really don't care about 0 because I can't have a radius of 0 and create a tin can or an aluminum can, and so I'm not going to include anything. This is out of my domain. Okay. I'm not going to have time to wrap this up, so I'll do that in the next video.